Hi, my name is Lakshya Jain and this is my video for solution of Maths End Semester Examination question 1. So let's get started. Okay, so the question is that in a room containing 20,000 cubic feet of air, 600 cubic feet of fresh air flows in per minute, and the mixture is made practically uniform and is exhausted at a rate of 600 cubic feet per minute. What is the amount of fresh air YT at any time if initially the amount of fresh air is 0, and the second part is that after what time will 90% of air be fresh. So let's jot down all the things that have been given to us. So the total capacity of the room, as I've written before already, is 20,000 cubic feet, right? So okay, now the inflow or rate of fresh air, that is the rate at which the fresh air is flowing, is given to us as 600 cubic feet. So the inflow rate of fresh air is given as 600 cubic feet per minute. This thing. And now the mixture is made practically uniform. This statement is also very important. We'll get to know why while we're solving this. And the rate of exhaustion is at a rate of 600 cubic feet per meter. Now this rate of exhaustion is actually the rate at which the entire air, the air that is being exhausted. So rate of air exhaustion, let's say, is given as 600 cubic feet per minute. Now using this, I'm going to calculate what is the rate at which the fresh air is getting exhausted. Now given that the total capacity of room is 20,000 cubic feet, so the fraction of air that gets exhausted is in basically 600 by 20,000, as the rate of air exhaustion is 600 cubic feet per minute, right? So the fraction of air that gets exhausted, and this is per minute, so this gives us 3 by 100. Right, now we know that YT is the amount of fresh air in the room at any instant. So this means that at any instant the rate of exhaustion of fresh air is nothing but the product of the fraction that we just calculated, the 3 by 100 fraction, that is the fraction of air that gets exhausted, multiplied by the amount of fresh air that is present at any instant in the room. Now this could also be better understood if we use a unitary method. Now since the air is uniform, 20,000 cubic feet of air gets exhausted. In 20,000 cubic feet of air, 600 cubic feet of air gets exhausted. So using unitary method, for 1 cubic feet of air, 600 by 20,000 cubic feet of air gets exhausted, and for YT, that is the amount of fresh air, 600 divided by 20,000 into YT gets exhausted. And this value is the same as I calculated here. So this is the rate of exhaustion of fresh air. Okay. Now, so now from according to the balance law, as it is called, the time flow or the rate of flow of fresh air, the net rate of flow fresh air is written as the inflow rate fresh air minus the exhaustion rate, the rate of exhaustion, in other words, for fresh air, right? So this net rate of flow is nothing but the derivative of y with respect to the time. So where y was the amount of fresh air at any instant. The inflow rate, as it was given, was 600 cubic feet per minute minus the exhaustion rate, which I calculated as 3 by 100 into y. So this now can be written as y derivative is 600 minus 0.03 y. Now this is an ordinary differential equation of first order, and it is a non-homogeneous linear differential order. So I'm gonna use a variable separation method in order to solve this differential equation. So let's get to that. Now dy by dt is 600 minus 0.03y. Now taking the RHS in denominator, that is the y terms the y below as a denominator, and dt at the RHS, and now I'm gonna integrate it with proper limits both sides. So this is from 0 to yt and 0 to a time t. So this gives us minus 1 upon 0.03 into log mod 600 minus 0.03y, and limits are 0 to y t, and this is equal to t minus 0. So this implies minus 1.0.03 log mod 600 minus 0.03 yt minus log mod 600, and this is equal to t. This is equal to t. So now this implies log mod 600 minus 0.03 yt divided by 600 can be written as minus 0.03 t. Okay. Now taking the log to the other side, 600 minus 0.03 yt divided by 600 can be written as, this goes to exponential 3. This goes to exponential. Now this implies that 600 minus 0.03 yt can be written as 600 e raised to the power minus 0.03 t, implying 0.03 yt is 600 e raised to the power minus 0.03 t minus 1. I have taken the 600 out common, and this gives us yt, and here's a minus sign here actually, and yt is 600 divided by 0.03, 1 minus e raised power minus 03t, taking the minus outside, and this implies yt is, this is 20,000, 1 minus e raised power minus 0.03 t. This is the amount of fresh air that is present in the room at any instant. So if we want to plot a rough graph, it's going to be something like this, very near to the x-axis, where x represents the time and y is the amount of fresh air. So this is going to be very near the x-axis, the amount of fresh air at any instant of time, right? So this solves our first part. The second part states that at what time will the yt be 90% of the total amount of air, that is of 20,000, or in other words, that is yt should be equal to 90 by 100 of 20,000. So let's substitute it in the equation that we had just found. So this implies 90 by 100 into 20,000, 90 by 100 into 20,000 is equal to 20,000, 1 minus e raised power minus 0.03 t, and 20,000 gets cancelled, 10. So this implies 0.9 is 1 minus e raised power minus 0.03 t. Now this implies e raised power minus 0.03 t is this 0.1, and this implies, taking log at both sides, 0.03 t is log of 0.1, and 0. Which can be written as minus log of 10, minus gets cancelled, and this implies t is natural log 10 divided by 0.03 t, and this basically gives us 76.7 minutes as our answer. So the answer for the first part, that the amount of fresh air at any instant is 20,000 multiplied by 1 minus e raised power minus 0.03 t, and for the second part, where we want to calculate the time at which the amount of fresh air is 90% of the total air, that is of 90% of 20,000, is 76.7 minutes.